Hello everyone, this is Group 8 of Division A from VIT Pune. Our topic is Instruction Pipeline Implementation. First of all, what is instruction pipeline? Instruction pipeline is a technique used in computer architecture to increase the performance of a processor by allowing the processor to execute multiple instructions simultaneously. Instruction pipeline implementation is basically a technique which is used in computer architecture, which involves breaking down the execution of an instruction into series of smaller steps, which can then be executed in parallel. In an instruction pipeline, the processor is divided into several stages, and each stage performs a specific operation on the instruction. So, like we have five stages: fetch stage, decode stage, execute stage, memory stage, and write back stage, which we'll be discussing in later part. By dividing the processor's work into smaller, more manageable pieces, instruction pipeline implementation allows for the parallel execution of instructions, resulting in increased throughput and faster execution. Then, benefits of instruction pipeline. First one is increased throughput. By dividing the processor's work into smaller, more manageable pieces, instruction pipeline implementation allows for parallel execution of instructions. This results in an increase in the number of instructions processed per unit time, thereby increasing the overall throughput of the processor. Second is faster execution. So, instruction pipeline implementation reduces the time taken to execute an instruction by allowing different stages of pipeline to work on different instructions at the same time. This results in faster execution of individual instructions and consequently faster overall performance. Next, we have reduced latency. The use of instruction pipeline implementation reduces the latency between the time an instruction is fetched and the time its result is written back to a register. This results in a reduction in the amount of time that the processor spends idle waiting for the instructions to complete. And last, we have flexibility. Instruction pipeline implementation allows for greater flexibility in processor design by enabling the use of different architectures and microarchitectures. This enables designers to tailor processors to meet specific performance requirements and applications.
And I will be explaining the stages of instruction pipeline. Detailed explanation for each stage of the instruction pipeline. Instruction fetch. In this stage, the processor fetches the next instruction from memory. The address of the instruction to be fetched is determined by the program counter register. The processor sends a memory read request to fetch the instruction from memory. The instruction is then stored in the instruction register so that it can be decoded in the next stage. Instruction decode. In this stage, the processor decodes the instruction and determines what operation needs to be performed. The instruction is also checked for any data dependencies with previously executed instructions. The instruction decoder reads the opcode and the fields of the instruction from the IR and generates the control signals required for executing the instruction. The decoder also identifies the source and destination registers and determines whether any data dependencies exist between the current instruction and the instructions in the pipeline. Execution. In this stage, the processor executes the operation specified by the instruction. This may involve arithmetic or logic operations as well as memory access or input output operations. The specific operation performed in this stage depends on the type of instruction being executed. For example, if the instruction is an arithmetic instruction, the processor may perform addition, subtraction, or multiplication in this stage. Memory access. In this stage, the processor accesses the memory to read or write data. This stage is only necessary for instructions that involve memory access. If the instruction involves reading data from memory, the processor sends a memory read request to retrieve the data from memory. If the instruction involves writing data to the memory, the processor sends a memory write request to store the data in the memory. Write back. In this stage, the processor writes the result of the operation back to a register. The result is written back to the register file, making it available for use by subsequent instructions. The specific register that is updated depends on the instruction being executed. For example, if the instruction is an arithmetic instruction, the result is written back to the destination register. Illustration of how each stage works with examples. Instruction fetch. In this stage, the processor fetches the next instruction from the memory. For example, let us consider the following instruction: add T0, T1, T2. The address of the instruction is determined by the program counter PC register. The processor sends a memory read request to fetch the instruction from memory at the address specified by the PC. The instruction is then stored in the instruction register IR so that it can be decoded in the next stage. Instruction decode. In this stage, the processor decodes the instruction and determines what operation needs to be performed. Let's continue with the example instruction from the previous stage. The instruction decoder reads the opcode and other fields of the instruction from the IR and generates the control signals required for execution of the instruction. The decoder also identifies the source and destination registers and determines whether any data dependencies exist between the current instruction and the instructions in the pipeline. In the case of the add instruction, the decoder identifies that it is an arithmetic instruction and that the registers T1 and T2 are the source registers and T0 is the destination register. Execution. In this stage, the processor executes the operation specified by the instruction. For the add instruction, the processor would perform the addition of the values stored in T1 and T2 and store the result in T0. Memory access. In this stage, the processor accesses the memory to read or write the data. This stage is only necessary for instructions that involve memory access. In the case of the add instruction, where there is no memory access involved, so this stage is skipped. Write back. In this stage, the processor writes the result of the operation back to a register. In the case of the add instruction, the result is written back to the destination register.
Pipeline. So hazards are situations that may arise in an instruction pipeline that can affect the correct execution of instruction or cause a delay in the pipeline stages. There are three types of hazards. First, structural hazards. Structural hazards occur when when two instructions require the same hardware resource at the same time. For example, if two instructions need to access the memory simultaneously, a structural hazard will occur. This can cause the pipeline to stall, which can result in significant performance penalty. Data hazards. Data hazards occur when there is an instruction dependence on the previous instruction that has not yet completed its execution. Data hazards can occur due to read after write, write after read, and write after write dependencies. Control hazards. Control hazards occur when there is a conditional branch instruction in the pipeline. The pipeline must decide whether to take the branch or not before it has fully decoded the branch instruction. This can result in a delay as the pipeline waits for the branch instruction to be resolved. Additionally, if the pipeline takes a wrong branch, the pipeline will need to be flushed and the instructions that have been fetched but not executed will need to be discarded. Techniques to handle hazard. There are several techniques used to handle hazards in instruction pipelines. Here, the two commonly used techniques are: first, forwarding. Forwarding is a technique used to handle data hazards in an instruction pipeline. It involves data directly from one stage of the pipeline to another to avoid stalls caused by data dependencies. The second instruction depends on the result of the first instruction. Without forwarding, the pipeline would need to stall until the result of the first instruction is written to the register file. However, with forwarding, the result of the first instruction can be passed directly to the second instruction without waiting for it to be written to the register file. Branch prediction. Branch prediction is a technique used to handle control hazards in an instruction pipeline. It involves predicting the outcome of a branch instruction to avoid stalls caused by control dependencies. There are two types of branch prediction. First, static branch prediction. This involves predicting the outcome of a branch based on the instruction opcode. For example, if the opcode is a conditional jump instruction, the pipeline can assume that the branch will be taken or not based on the condition. Second, dynamic branch prediction. This involves predicting the outcome of a branch based on the history of the program. There are several types of dynamic branch prediction techniques, such as two-level adaptive branch prediction and neural branch prediction. These techniques use the history of the branch outcomes to predict the outcome of the future branch.
So now design considerations for implementing an instructions pipeline. So we consider seven considerations, and one is instruction set architecture. As we know, it is known as ISA. And the second one is pipeline stages, and the third one is hazards, and the fourth one is memory hierarchy, and the fifth one is clock speed, and the sixth one is cost, and the seventh one is debugging and verification. Now we come over superscalar pipeline. A superscalar pipeline is designed to execute multiple instructions in parallel by allowing multiple instructions to enter the pipeline at the same time. And now the second one is vector pipeline. A vector pipeline is designed to improve the performance of pipelines by allowing instructions to operate on multiple data elements simultaneously.
Everyone, myself Anubhav Pandey and I am here to explain about pipeline and non-pipeline processors. So compared to non-pipeline processors, pipeline processors can offer several performance benefits including increased throughput, reduced latency and improved efficiency. However, there are also some limitations and drawbacks to pipelining that can affect performance. These include pipeline stalls and hazards, increased complexity and overhead. So basically, pipeline stalls and hazards. Pipelining can introduce hazards and stalls in the pipeline which can reduce the performance gains of pipelining. Increased complexity. Pipelining introduces additional complexity into the processor design which can increase design and implementation time and also increase the power consumption. And overhead. Pipelining introduces additional overhead in terms of hardware required to implement the pipeline. This can increase the cost of the processor. Now, there are also some challenges in achieving optimal performance with the instruction pipelines. These challenges include hazard detection. Overhead and resource constraints, instruction scheduling and dependencies, memory access and cache utilization, pipeline depth and branch prediction accuracy, compiler optimizations, and so on. So basically now the conclusion we can draw about is that instruction pipeline implementation can provide several benefits to processor performance, including increased throughput, reduced latency and improves efficiency. However, there are also several challenges to achieving optimal performance with instruction pipelines. These challenges are not that easy to overcome, and so as to overcome them, there are several other future trends for developments in instruction pipeline design, including increased pipeline width, increasing pipeline depth, dynamic pipeline turning, hybrid pipeline, machine learning based pipeline organization, heterogeneous computing, and overall instruction pipeline design is likely to continue to evolve and improve with a focus on balancing performance, efficiency, and flexibility to meet the diverse needs of modern computing workloads. Thank you.